In this video, we have another matrix problem, and we're going to look at how do we rotate this matrix 90 degrees clockwise. And so clockwise will go this way. So this top row ends up being the last column. This middle row, second row, becomes the middle column. And then this last row becomes this first column. As with any matrix problem or array problem, we often want to strive to do it in place. And often with interview problems, they give you these structures on purpose because arrays are often really simple to deal with. They're going to give you it on purpose to see how you creatively use them. And whether you're overwriting entries to stay in constant space, whether you are staying in place, and again, maybe using temporary variables to shift things around, the whole point is to see how can you efficiently optimize these things within the bounds of the structure. So we want to do this in place. We can easily create a new matrix. We can easily just copy over. Start here, iterate, copy that over, copy that over. We can do that with for loops, right? But how can we do this in place? And whenever we're dealing with something like this, we want to trace where things are going. If we can trace where things are going, then we can eventually see what is the pattern that we need to follow in order to get these numbers where they need to be. Let's trace one number and see where it leads us. So we're going to trace the 1. The 1 is sitting right there, and we see that it ends up over there. Maybe we want to just trace the top row. So we're going to start at the 1, and then let's trace the next number. Let's trace the 2 and see where that ends up. Okay, that's interesting. We see that it's kind of like a rotation. We see that these items in the layer are moving to another layer, just differently oriented, and this makes sense. So let's trace the 3. Let's trace the last number. We want to move the 3 from that position to the final position, and we see it's right there. And what you kind of notice is that it's taking their layers to this. And we saw this in other matrix problems, and if layers can be treated independently, then there's a way we can set up the iteration so that we can process layer by layer and then run the exact same subroutine. This is very well modeled recursively. Whenever we have something where we can repeat things with different state change, we often can model it recursively, right? We've seen this with other problems. With this problem, we could do it recursively. We're just going to look at the iterative way. That's the way it's implemented in the code sample. The layers are there's going to be 4 key interchanges here. We're just seeing one of the key interchanges, but there's actually 4 critical segments to track, and this is what they look like. If we continued along the same line of thinking, and we tracked the corners, so let's track the corners, we see that every single one of these layer operations is actually a 4-way interchange. The 1 ends up right here. That's 3 ends up down there. And then this 9 ends up over here. And then this 7 ends up there. So that's one interchange. And this layer is not finished. There's a few more items. So we're going to go one more item. So we're going to move this top pointer over here. We're going to move this pointer top right down here. And then we're going to move this pointer over here. And then we're going to move this pointer over here. And so now what just happened? This top pointer's scanning this way. This right pointer scanning this way, this bottom pointer's started here, it's scanning this way, and then this pointer down here is scanning up to here. So each of these are gonna do this. That's where the top's gonna go, that's what the right will cover, that's what the bottom will cover, and that is what the left boundary will cover, just so these guys aren't overlapping. We only wanna do interchanges and not re-interchange. So where do these end up? We see the 2 ends up over here. And notice, this guy goes right there. And then this guy goes right there. That's 6. That 6 jumps there. And then we see the 8 goes here. And then we see the 4 goes there. And now we do this exact same routine except on the innermost layer. And we can't do anything here. We can't even go to this innermost layer, so we would break. We would stop iterating. And that is it. That would perform the rotation of this matrix. That would complete it, right? And if we run this same routine at every layer because we established layers are independent, then that means that the whole matrix, this will cause the rotation to happen. So this is one way to view it. There's also another way to view this. This is the second approach. If we track where this row goes, what happens to that row? That row gets laid out. It gets laid out and it ends up over here. And this is really esoteric. You would probably not get this in an interview, but I thought this solution was interesting because it's related to linear algebra and matrices transposes. The proposition behind this idea is flip all of the rows. So flip the image vertically. So if we flip the image vertically, it'd end up like this. So we would end up with this. And then there's something called the transpose of a matrix. What the transpose does is every row becomes a column. So the first row becomes the first column. And if we notice something in the resulting matrix, the first column is exactly what the first row is here. And then the second row here in this vertically flipped matrix is the second column. And then the third row is the third column. And so this is more of, and it's not really esoteric. You'd have to know linear algebra and understand matrix transposes and kind of see this pattern. And if you've already seen that, then you might see this immediately. If not, you completely wouldn't see it because it's not really something accessible with intuition. It's just something you'd have to see. So don't worry about this one as much. The layer interchange is a lot more accessible. That's something you could probably figure out if you thought about this for at least like half an hour. That is one way to approach this problem. And we're going to look at the code for the interchange approach. So let's look at that. So we're going to do all of this in place. So we're not going to return a new matrix. We're going to perform destructive writes and swaps on the actual matrix. We're going to keep a variable. We're just going to call it size, but it's going to denote the size of the array minus 1, which is the last index. Okay, and then we need to think, how many layers are there in this matrix? How many dimensions can this matrix is n by n. So it's going to either be odd or even in dimension. So let's look at both cases. Okay, so what is the height of each of these matrices? The height is 3 in this case, the height is 4. So how many layers are there? There's one layer. There's one layer that we would want to do, and then we don't touch the inside. So how many iterations do we want to do? Only process one layer in this case. Okay, just in this specific case, just one layer. And then in this case, we want to process 2. We want to process 2 layers. So what we can say is, in this case, we can just do 4 divided by 2. That's going to be 2. That's how many layers. But in this case, it's a bit trickier. Do we want to divide by 2? 3 divided by 2, what does that equal? That equals 1.5. But remember, these are integer types, and we can't have a floating point value. That can't be represented with this type. So it's just going to, it's not even going to be able to represent the decimal place. So it just becomes 1. And that's actually exactly what we wanted, 1 layer. And if this was 5, we'd do 5 divided by 2, and then that would be 2.5. And if we truncate the decimal, that's just 2. And what does a 5 by 5 look like? It looks like that. And so let's highlight the layers. And how many layers do we want to process? 1, 2. Then there's a center element. So it's 2. And that's correct. That's what we wanted. So now we know what our outer iteration looks like. Now we know how to count the layers. So we can use this layer as an offset. If we want to maybe say the top boundary, well, that's going to be denoted by the layer. And then the bottom boundary, we can say last index, or the matrix size, last index, minus the layer. Right now, the size minus the layer, so the size minus what layer we're on, is going to be just size, because size minus 0, which is where layer starts, is just size. That's the last index, right? And if it's the last index, that means what happens when the layer is 1? It's going to pull it in. It'll pull it upwards. We're trying to set up iteration variables to allow us to string things together so that we can get the right guys and interchange them. Now, we're going to need another iteration variable to actually move within the layer. We need to move within these offsets. So we're going to create an iteration for that. So this variable I is just what we're going to use to iterate through the layer. So if we had a left boundary, it's going to start at 0 since layer is 0. And then we're going to go all the way to size minus layer, the last index. And this is n by n. So the last index is the same as the last column index and the last row index. So that's going to bring us all the way to the end. And then when layer is 1, that's going to shrink both sides together because now layer is going to start at 1 and it's going to go to size minus 1, right? The last index previous minus 1, which is the second to last. And this is going to give us the ability to change. We ask ourselves, where is the top corner? Well, think about this. The top corner, there's going to be a scan happening, right? There's 4 scans. There's a scan here. There's going to be 4 pointers that start in these corners of the layer, and they're going to scan. There's going to be a top scanner, right scanner, bottom scanner, and a left scanner, like we saw before. The top scanner, where is that? That's going, well, let's ask ourselves, what changes? What changes? The column changes. So the row is going to be static. And what row are we in? We're in layer. Layer is the first row. It's index 0. Layer is 0. So our row will index in, and that'll get us the row. But then what is the column, right? Remember the column's the changing factor. We parameterized it here. The layer is 0. Again, we use that to denote rows when we were indexing into rows, but it actually can give us the column as well. We're in column layer, right? But do we want to say that we're in column layer? Well, layer is going to change in the outer loop, right? This I is what is going to iterate us through this row. So that means we're going to use the I. The I goes from index 0 all the way to the last index. And in this case, it goes from index 0 to size minus 0, which is just size, which is the last index. So 0 to the last index. Column goes where we want it, top row. So you can see that really all this is about is your ability to conceptualize indexing in your head. This is a really tough test. I mean, this would be under pressure to understand how to get the index right and get the iteration right with this. And it's just a matter of really being keen on keeping that vision, keeping that image in your mind of this image, what we're trying to do. So now we're gonna grab the top, the right boundary. This is the pointer that'll walk the right boundary. And so what's the changing factor? Changing factor is the row. And what is the row gonna go from? It's going to go from index 0 all the way to the last index. We actually saw that. The row, except we parameterized the column in that first instance because that was changing. Now we parameterized the row. And so what stays constant? The column we're in. What column are we in? We're in size minus layer. And the size is the last index. The layer right now is 0. So that's going to give us exactly what we want, the last column. And now let's look at the, now we need to get this guy, the bottom. So we need to think about this. What is the row? What is the column? And what is changing? That's the key thing to think about. The row is consistent. The bottom guy is going to scan this way. So the row, what is this? It's going to be layer, or it's going to be size, last index, minus layer. So that's the row. And then we need to ask ourselves, what is the column going to be? The column is the changing factor. Therefore, that I is the iteration variable we want to parameterize with, right? So we're going to say the column is going to start all the way over here. It's going to come back this way. If we want to come backwards, we can use a minus sign. So last index size minus this I. The I is going to start at 0, so that means our column is going to be all the way over here. It'll bring us this way. That's exactly what we want. So size minus I. Okay, so we completed that and we got the top corner, we got the right corner for the right scan, we got the bottom corner for this bottom scan, and then this left guy for the left scan. So we need to get him. And so at this point, we should be pretty fluent in how these are being indexed. So what's the changing factor? We need to think about row call, which is changing. The row is changing. We start at the last row, and it's parameterized by I. That means we're going to take the size and subtract it by I. The size is our anchor. I is what's changing. It's going to give us modulated rows. And then the column is going to be the layer, right? The layer we are in, because if we're in over here, that's the layer offset. So we'll just say layer. And now, at this point, we have everything we need to perform an interchange. What is the interchange? Remember, let's number these. If these are where our pointers start, 1 goes to where 2 is. 2 goes to where 3 is. 3 goes to where 4 is. 4 goes to where 1 is. And so that's the rotation. That's what it would look like. So that's the rotation we're going to do here. So this top guy, we know what he looks like. That's what he looks like. That's his position. We pulled him out just so we could set him. And the reason we pulled this variable out is so that we can move the top to someone later. So what gets set into this top index? If we think about it, remember who is over here? The left boundary walker, this guy who starts in the bottom left corner, that's what ends up in the top guy. So we just say left. So this is the interchange. We pull these guys out just so we can move them around and just overlap. We overwrite what was previously in their positions, but we're performing the rotation element by element in the layer we're in. When we're done with the layer, do the same thing on the next layer, element by element, four time temp swaps. So now we're gonna do, we set the top guy. Now the top guy is 4. And remember, in our temp, we still have the top, so let's keep track of those. So right now, what we just did is we overwrote the top. We overwrote this guy, the guy scanning the top, with the value of left, 4 moved there. And so we're gonna do the same thing. We're going to take the right, so that right there is the right. We're going to set that to top. So the guy scanning the right, which he starts there, he's gonna get the value of top, which is 1. And now let's consider what the guy right here is going to get, bottom. Well, bottom is going to get what was at right. This right scanner is gonna be what bottom becomes. So right is 2, and then that's right. And then what does the guy over here, the left position, become? He becomes what bottom was, right? He just becomes what this bottom, he just becomes the bottom, which is 3. And so that's all. this is the four-way interchange. We pulled everyone out into temps, and then we went around, and well, we didn't go around, we just set the values one position over. The top went into over here, this guy went over here, this guy went over here, this guy went over here, and then that's a 90-degree rotation. This is exactly what we wanted with our values. So this is the problem of rotating a matrix 90 degrees clockwise. It'd be the same procedure counterclockwise, except we would just need to invert the way that we're doing this. We need to go the other way, but it could still be done layer by layer because the matrix would still be n by n. It'd be the same procedure. So there's code for this approach and there's code for the transpose approach in the description for both of those if you want to review them. As for time complexities, we're going to be visiting every one of the elements. In the case where we don't visit that center element, we're still going to asymptotically be doing m times n time because we're visiting big O m times n elements, doing constant work for each of them. And in terms of space, we're not creating an auxiliary structure. We're just doing reads and constant time updates. So this is constant space and m times n time. So that's the complexity for this solution.